The lesson for this video is binary operations. Let's look at the objectives for the lesson. At the end of the lesson, you should know and understand the properties of binary operations, and you should be able to solve questions on binary operations. Now, let's learn more about binary operations. In mathematics, the basic operators are addition, subtraction, multiplication, and division. And these operators are used to combine two or more numbers to give us another number. So for example, if we have 3 plus 4, the operator addition combines 3 and 4 to give us 7. If we have, let's say, 4 minus 3, the operator subtraction combines 3 and 4 to give us 1. The same goes for multiplication and division. These four basic operators have standard definitions that are known worldwide. So 3 plus 4 means that we should add 3 to 4. 4 minus 3 means that we should subtract 3 from 4. These meanings are known and accepted worldwide. What we will learn in our lesson on binary operation is that there are other operators apart from these four basic ones. For example, we can have the operator star, we can have the operator delta, you can have a circled dot. These are operators that are also used to perform mathematical computations. But unlike these four basic operators that have standard definitions that are known and accepted worldwide, these other operators do not have such definitions. When you are required to perform a computation or a calculation with any of these operators, the definition of the operator will be given to you. So for example, let's say you are required to use the operator star. The definition of the operator star will be given to you. For example, let's say A star B is equal to A plus B minus AB. This is the definition of star in this instance. So using this definition, we can find the value of 3 star 2. When we compare A star B to 3 star 2, we can see that A is equal to 3 and B is equal to 2. So if A star B is equal to A plus B minus AB, then 3 star 2 will be equal to 3 plus 2 minus 3 times 2. 3 plus 2 will give us 5. 3 minus 2 gives us 6. 5 minus 6 gives us -1. So using the definition of the operator star, we have been able to combine the numbers 3 and 2 to get a result which is -1. So in our study on binary operations, whenever we are required to perform an operation with any of these operators, the definition of the operator will be given to us. Let's solve some questions to throw more light on this. Here is the first question. There's a multiple choice question, so we will solve it and then we will pick the right option. The question says that a binary operation delta is defined on the set of real numbers by A delta B is equal to A raised to the power B. Find the value of 3 delta -2. So the definition of the operator delta is A delta B is equal to A exponent B. We want to find 3 delta -2. So here we will have to compare A delta B to 3 delta -2 to get the values of A and B. By comparison, we can clearly see that A is 3 and B is -2. So if A delta B is equal to A exponent B, then 3 delta -2 will be equal to A, which is 3, exponent B, which is -2. From indices, we know that 3 exponent -2 is equal to 1 divided by 3 exponent 2. And 3 exponent 2 gives us 9. So 1 divided by 3 exponent 2 gives us 1 divided by 9. So 3 delta -2 is 1 divided by 9. When we look through the options, we can see that the correct one is C. Let's consider the next question. A binary operation is defined by A star B is equal to A squared minus B squared plus AB, where A and B are real numbers. Evaluate square root of 2 star square root of 3. The definition of the operator star is A star B is equal to A squared minus B squared plus AB. And we want to find square root of 2 star square root of 3. So by comparison, we can see that A is square root of 2 and B is square root of 3. So square root of 2 star square root of 3 will be equal to square root of 2 squared minus square root of 3 squared plus square root of 2 times square root of 3. Here the square and the square root will be gone. The square and the square root will be gone here. So this will give us 2 minus 3 plus square root of 2 times square root of 3. From our lesson on sets, we know that this will give us square root of 6. 2 minus 3 gives us -1. So we have -1 plus square root of 6. And when we rearrange this, we are going to have square root of 6 minus 1. When we look through the options, we can see that the correct one is option B. Let's consider the next question. A binary operation is defined on the set of real numbers by A delta B is equal to square root of A plus square root of B times square root of A minus square root of B. Find the value of x if x delta 2 is equal to 1. The definition of the binary operation is A delta B is equal to square root of A plus square root of B times square root of A minus square root of B. The equation given to us is x delta 2 is equal to 1. Let's find x delta 2. When we compare A delta B to x delta 2, we can see that A is x and B is 2. So x delta 2 will be equal to square root of x plus square root of 2 times square root of x minus square root of 2. Let's open the bracket here. We are going to have square root of x times square root of s gives us x. Square root of x times negative square root of 2 gives us negative square root of 2x. Then square root of 2 times square root of x gives us square root of 2x. Square root of 2 times square root of -2 gives us 2. So as we can see, negative square root of 2x, positive square root of 2x will be gone. And so we will be left with x minus 2. From the equation, x delta 2 is equal to 1. And from the definition of the binary operation, x delta 2 is equal to x minus 2. So we can say that if x delta 2 is equal to 1 and x delta 2 is x minus 2, then x minus 2 is equal to 1. X minus 2 is equal to 1, so x will be equal to 1 plus 2, and 1 plus 2 gives us 3. When we look through the options, we can see that the correct answer is A. Let's consider the next question. A binary operation times is defined on the set of real numbers by A times B is equal to A plus B root 2. Find 2 times -3 times 5. Because this is a binary operation, we can compute only 2 numbers at a time. So we will begin with what is in the bracket. 2 times negative 3. The definition of the binary operation is A times B is equal to A plus B root 2. We are going to compute 2 times negative 3. By comparison, we can see that A is 2 and B is negative 3. So 2 times negative 3 will be equal to 2 plus negative 3 root 2. And this will give us 2 minus 3 root 2. So what is in the bracket, which is 2 times negative 3, gives us 2 minus 3 root 2. So then 2 times negative 3 times 5 will be equal to 2 times negative 3 is now 2 minus 3 root 2. So 2 minus 3 root 2 times 5. We can now compute these two. The definition of the binary operation is A star B is equal to A plus B root 2. So if we are computing 2 minus 3 root 2 times 5, then it means that 2 minus 3 root 2 is now A and 5 is now B. So if we substitute this into the definition, we are going to have A, which is 2 minus 3 root 2, plus B, which is 5 root 2. Negative 3 root 2 plus 5 root 2 gives us 2 root 2. So 2 minus 3 root 2 times 5 will be equal to 2 plus 2 root 2. When we look through the options, we can see that the correct one is B. Let's consider the next question. A binary operation star is defined by A star B is equal to A plus 2B divided by 3. Find the value of M if 3 star M star 4 is equal to 3. The definition of the binary operation is A star B is equal to A plus 2B divided by 3. The equation given to us is 3 star M star 4 is equal to 3. So here we will compute what we have on the left hand side and then equate it to the right hand side, which is 3. When you look at the left hand side, we have 3 star M star 4. But because this is a binary operation, we can compute only two numbers at a time. So we will begin with the one in the bracket, which is M star 4. So what is M star 4? When we compare A star B to M star 4, we can see that A is M and B is 4. And so this will give us A, which is M, plus 2B, and B is 4. So 2 times 4 divided by 3. 2 times 4 is 8. So this is going to give us M plus 8 divided by 3. So our M star 4 is M plus 8 divided by 3. And so 3 star M star 4 will be equal to 3 star M star 4 is now M plus 8 divided by 3. So we are going to have 3 star M plus 8 divided by 3. We can now compute 3 star M plus 8 divided by 3. When we compare 3 star M plus 8 divided by 3 to A star B, we can see that 3 will be A, and then M plus 8 divided by 3 will be B. So when we substitute this into the definition, we are going to have A, which is 3, plus 2 times B, which is M plus 8 divided by 3, all divided by 3. Don't forget that 3 star M star 4 is equal to 3 star M plus 8 divided by 3. And we have found out that 3 star M plus 8 divided by 3 will give us 3 plus 2 times M plus 8 divided by 3, all divided by 3. So we can say that 3 star m star 4 is equal to 3 plus 2 times m plus 8 divided by 3, all divided by 3. This is what we have on the left hand side of the equation, and we know that from the equation 3 star m star 4 is equal to 3. So we can say that 3 plus 2 times m plus 8 divided by 3, all divided by 3, is equal to 3. We can now solve this linear equation for the value of m. I'll multiply both sides by 3. When I do that, 3 and 3 will cancel each other out. And so this will give us 3 plus 2 times m plus 8 divided by 3 is equal to 9. I'll send 3 over to the right hand side. When I do that, I'm going to have 2 times m plus 8 divided by 3 is equal to 9 minus 3. 9 minus 3 gives us 6. So we are going to have 2 times m plus 8 divided by 3 is equal to 6. I'll multiply both sides by half. So I'll multiply the left hand side by half and the right hand side by half. When I do that, 2 and 2 will be gone. Half times 6 will give us 3. So we are going to have m plus 8 divided by 3 is equal to 3. I'll now multiply both sides by 3 to remove the fraction. So I'll multiply the left hand side by 3 and the right hand side by 3. 3 and 3 will be gone. 3 times 3 gives us 9. So we are going to have m plus 8 is equal to 9. And so m will be equal to 9 minus 8, which is 1. When we look through the options, we can see that the correct one is C. We have considered about 5 examples on the concept of binary operations. Now, let's learn about the properties of binary operations. In this lesson, we are going to consider the following properties of binary operations: closure, commutative, associative, distributive, identity, and inverse. We will begin with closure. The closure property. If the binary operation star is defined on the set R of real numbers and all the results produced by star belong to R, then star is said to be closed under R. So if a given binary operation is defined on a set and all the results produced by the binary operation belongs to the set, then the binary operation is said to be closed under the set. For example, in the table below, the binary operation is star and it is defined on the set T with members A, B, and C. From the table, we can see that A star A gives us C, A star B gives A star C gives B, B star A is A, B star B is B, and B star C is C. C star A is B, C star B is C, and C star C is A. As you can clearly see, all the results produced under the binary operation are either A, B, or C, and the members in set T are A, B, and C. So all the results produced under this binary operation can be found in set T. So we can say that the binary operation star is closed under set T. Let's solve some questions on the closure property. The binary operation star is defined by m star n is equal to half times m minus n. Form a table of the operation on the set S with members 2, 4, 6. State with reason whether or not star is closed under S. So here we are going to form a table for the binary operation star on the set 2, 4, 6. So we will draw a table with 4 columns and 4 rows. In the first column, we will have star, 2, 4, and 6. And the first row, we have star here, 2, 4, and 6. So here we have to fill the table. We are going to fill the table using the definition of the binary operation. The definition of the binary operation is m star n is equal to half times m minus n. So using the definition, 2 star 2 will be equal to half times. When we compare 2 star 2 to m star n, m will be 2 and n will also be 2. So you are going to have half times 2 minus 2. 2 minus 2 gives us 0. So half times 0 gives us 0. So 2 star 2 is 0. 2, the next one will be 2 star 4. By comparison, m will be 2 and n will be 4. So you are going to have half times 2 minus 4. 2 minus 4 gives us negative 2. So half times negative 2 will give us negative 1. So 2 star 4 gives us negative 1. The next one will be 2 star 6. So by comparison, m will be 2 and n will be 6. So we are going to have half times 2 minus 6. 2 minus 6 is negative 4. Half times negative 4 gives us negative 2. So m star 6 gives us negative 2. Let's go on to the next one. The next one will be 4 star 2. 4 star 2. By comparison, m will be 4 and n will be 2. So we are going to have half times 4 minus 2. 4 minus 2 is 2. Half times 2 will give us 1. So 1. The next one will be 4 star 4. 4 star 4. By comparison, m will be 4, n will also be 4. 4 minus 4 gives us 0. Half times 0 gives us 0. So 4 star 4 is 0. The next one is 4 star 6. 4 star 6. By comparison, m is 4, n is 6. So we are going to have half times 4 minus 6. 4 minus 6 gives us negative 2. Half times negative 2 gives us negative 1. So 4 star 6 gives us negative 1. The next one is 6 star 2. 6 star 2. So by comparison, m will be 6, n will be 2. So we have half times 6 minus 2. 6 minus 2 is 4. So half times 4 gives us 2. So 6 star 2 gives us 2. The next one is 6 star 4. By comparison, m will be 6, n will be 4. So we are going to have half times 6 minus 4. 6 minus 4 is 2. Half times 2 gives us 1. And the last one is 6 star 6. By comparison, m will be 6, n will be 6. So we have half times 6 minus 6. 6 minus 6 is 0. Half times 0 gives us 0. So as you can see here, the results that we produced under the binary operation star are 0, negative 1, negative 2, 1, 0, negative 1, 2, 1, 0. We have some members in this result that are not in set S. For example, 0 is not in set X, negative 1 is not in set X, negative 2 is not in set S, 1 is not in set S. The only result here that is in set S is 2. So because there are some members that are produced by the binary operation star that are not in set S, we can say that the binary operation star is not closed under set S. Let's consider the next example. A binary operation delta is defined on the set T with members 1, 2, 3, 4 by A delta B is equal to A plus B minus AB, where A and B belongs to delta. A. Copy and complete the table. B. Is T closed with respect to delta? Let's begin with the first part of the question, which says that we should copy and complete the table. So here, part of the table has been filled for us, and so we have to find the missing pieces. The first one is this, and we are going to get this by computing for 2 delta 2. The definition of the binary operation is A delta B is equal to A plus B minus AB. So 2 delta 2 will be equal to, by comparison, A will be 2 and B will also be 2. So 2 plus 2 minus 2 times 2. 2 plus 2 is 4. 2 times 2 is 4. So we are going to have 4 minus 4, which gives us 0. So 2 delta 2 is 0. The next one will be 3 delta 3. So let's find that. 3 delta 3. By comparison, A will be 3 and B will be 3. So that will be 3 plus 3 minus 3 times 3. And this will be equal to 3 plus 3 is 6. 3 times 3 is 9. So we are going to have 6 minus 9, which will give us negative 3. So we have this to be negative 3. The next one will be 3 delta 4. So 3 delta 4. By comparison, A will be 3, B will be 4. So we have 3 plus 4 minus 3 times 4. 3 plus 4 is 7. 3 times 4 is 12. So we are going to have 7 minus 12. And 7 minus 12 gives us negative 5. So 3 delta 4 gives us negative 5. The last one will be 4 delta 3. 4 delta 3. By comparison, A will be 4 and B will be 3. So 4 delta 3 will be 4 plus 3 minus 4 times 3. 4 plus 3 gives us 7. 4 times 3 gives us 12. So 7 minus 12 will give us negative 5. So 4 delta 3 gives us negative 5. We have completed the table. The next part of the question says that, is T closed with respect to delta? When we look through the table, we can see that there are some results that are produced by the binary operation delta that are not in set T. So for example, we have 0, that's not in set T. We have negative 1, negative 2, negative 3, negative 5, negative 8. They are all not in set T. And so we can say that T is not closed with respect to delta. A binary operation is said to be closed under a given set when all the results produced by the binary operation can be found in that set. Let's move on to the next property, which is the commutative property. If the binary operation star is defined on the set R of real numbers, then star is said to be commutative when A star B is equal to B star A. So if the binary operation star is commutative, then when you compute for A star B, the results should be the same as when you compute for B star A. Let's apply this to solve some questions. A binary operation star is defined on the set R of real numbers by P star Q is equal to P squared plus Q squared minus PQ. Determine whether or not star is commutative. We have learned that if star is commutative, then P star Q should be equal to Q star P. So here, what we have on the left-hand side, which is P star Q, should be the same as what we have on the right-hand side, which is Q star P. What is P star Q? The question tells us that P star Q is P squared plus Q squared minus PQ. We can find Q star P because we have the definition. When we compare P star Q to Q star P, we can see that P will be Q and Q will be P. So Q star P will be equal to Q squared plus P squared minus QP. Now we have to compare whether P star Q is equal to Q star P. Let's compare. On the left-hand side, we have P squared. On the right-hand side, we have P squared, which is equal. On the left-hand side, we have Q squared. On the right-hand side, we have Q squared, which is the same. On the left-hand side, we have negative PQ. On the right-hand side, we have negative QP. We know from multiplication that PQ is the same as QP. So negative PQ is the same as negative QP. So as you can clearly see, what we have on the left-hand side is equal to what we have on the right-hand side. So P star Q is equal to Q star P. Since P star Q is equal to Q star P, we can say that the binary operation star is commutative. Let's consider another question. A binary operation delta is defined on the set R of real numbers by P delta Q is equal to P squared minus 2PQ. Determine whether or not the binary operation delta is commutative. We have just learned that if delta is commutative, then P delta Q should be equal to Q delta P. So what we have on the left-hand side should be the same as what we have on the right-hand side. From the question, we know that P delta Q is P squared minus 2PQ. We can find Q delta P. By comparison, we can see that P is Q and Q is P. And so Q delta P will be equal to Q squared minus 2QP. Now let's compare P delta Q to Q delta P. As you can clearly see, we have negative 2PQ here. Here, we have negative 2QP. Negative 2PQ is the same as negative 2QP. But on the left-hand side, we have P squared. On the right-hand side, we have Q squared. P squared is not the same as Q squared. So here, P delta Q is not equal to Q delta P. And so, since P delta Q is not equal to Q delta P, the binary operation delta is not commutative. Let's consider the next question on the commutative property. The table below shows the operation delta on the set A, B, C, and D. State whether or not the operation is commutative. We have learned that if delta is commutative, then A delta B should be equal to B delta A. You can pick any two variables, it's going to work. So you can pick C delta D is equal to D delta C, or B delta A is equal to A delta B, or D delta B is equal to B delta D. It's the same thing. Any one that you pick should work. So here I'm picking A delta B should be equal to B delta A. So I'll come to the table and then find A delta B. From the table, A delta B is C. Now let's find B delta A. From the table, B delta A is also C. As you can clearly see, C is equal to C. And so A delta B is equal to B delta A. And so because A delta B is equal to B delta A, the operation delta is commutative. We have considered 3 questions on the commutative property. Let's move on to the next property, which is the associative property. If the binary operation star is defined on the set R of real numbers, then star is said to be associative when A star B star C is equal to A star B star C. So if star is associative, then A star B in one bracket star C should be equal to A star B star C in one bracket. Let's apply this to solve some questions. Let's consider the first question. A binary operation star is defined on the set R of real numbers by x star y is equal to x plus y plus 6, where s and y belongs to the set of real numbers R. Determine whether or not star is associative. So we are going to determine whether or not the binary operation star is associative. And the definition of star is s star y is equal to x plus y plus 6. We have just learned that if star is associative, then x star y star another number. So here let's use z. So s star y star z should be equal to s star y star z in one bracket. So here we will compute what we have on the left hand side, then we compute what we have on the right hand side. After that, we will compare and see whether they are the same thing. Let's begin with the left hand side. On the left hand side, we have s star y star z. The question tells us that s star y is x plus y plus 6. So s star y star z will be equal to s star y is x plus y plus 6. So we have x plus y plus 6 star z. We can now compute s plus y plus 6 star z. So by comparison, s plus y plus 6 becomes x and z becomes y. So if we substitute this into the definition, x is now x plus y plus z. And y is now z, then plus 6. This will give us x plus y plus z plus 12. So it means that what we have on the left hand side, which is x star y star z, is equal to x plus y plus z plus 12. Let's compute for what we have on the right hand side. On the right hand side, we have x star y star z. So let's deal with what is in the bracket first, y star z. When we compare y star z to x star y, we can see that y is x and z is y. So if we substitute this into the definition, we are going to have y plus z plus 6. Okay, so we can now find x star y star z. Y star z is y plus z plus 6. So x star y star z will be equal to x star y plus z plus 6. Okay, we are going to compute for this. Now when we compare this to x star y, we can see that x is x and y plus z plus 6 is y. So if we substitute this into the definition, we are going to have x, which is x, plus y, which is y plus z plus 6 plus 6. And so when we simplify this, we are going to have x plus y plus z plus 12. So what we have on the right hand side, which is x star y star z, is x plus y plus z plus 12. So now let's compare what we have on the left hand side to what we have on the right hand side. What we have on the left hand side is x star y star z, which is x plus y plus z plus 12. And what we have on the right hand side is x star y star z, and that is x plus y plus z plus 12. So by comparison, we can see that x star y into bracket star z is equal to x star y star z into bracket, and so the binary operation star is associative. Let's consider the next question. The binary operation delta is defined on the set of non-zero rational numbers by a delta b is equal to a plus b divided by ab, where a and b are not equal to 0. Determine whether delta is associative. The definition for the binary operation is a delta b is equal to a plus b divided by ab. We have learned that if delta is associative, then a delta b into bracket delta c will be equal to a delta b delta c into bracket. So here we will compute what is on the left hand side, and then we will compute what is on the right hand side, and then afterwards we will compare our answers to see whether they are the same. Let's begin with what is on the left hand side. On the left hand side we have a delta b into bracket delta c. So you begin with what is in the bracket, but what is in the bracket is a delta b, and from the definition of the binary operation, a delta b is equal to a plus b divided by ab. So a delta b delta c is equal to a plus b divided by ab delta c. Now we can compute this. The definition of the binary operation is a delta b is equal to a plus b divided by ab. So if we compare a delta b to a plus b divided by ab delta c, we can see that a plus b divided by ab is a and c is b. So when we substitute this into the definition of the binary operation, a plus b divided by ab delta c will be equal to, the numerator is a plus b, and we have seen that a is a plus b divided by ab, and b is c. So on the numerator, we are going to have a plus b divided by ab plus c, divided by, on the denominator, we have ab, that is a times b, and a is a plus b divided by ab, and c is b. So we are going to have a plus b divided by ab times c. Let's simplify this. When we simplify what we have in this bracket, we are going to have a plus b plus abc divided by ab. When we simplify this, we are going to have c times a plus b divided by ab. From fractions, we know that this will give us a plus b plus abc divided by ab times ab divided by c times a plus b. So ab and ab will cancel each other out, and so we are going to have a plus b plus abc divided by ac plus bc. This is what we have on the left hand side. Now let's compute for the right hand side. On the right hand side we have a delta b delta c into bracket. So we are going to deal with what is in the bracket first. What we have in the bracket is b delta c. So we have to compute this using the definition of the binary operation. The definition of the binary operation is a delta b is equal to a plus b divided by ab. So if we compare a delta b to b delta c, we can see that b will be a and c will be b. So b delta c will be b plus c divided by bc. So a delta b delta c into bracket will give us a delta b plus c divided by bc. Now let's compute this. So we will compare this to the definition. From the definition, we have a delta b is equal to a plus b divided by ab. So we will compare a delta b plus c divided by bc to a delta b. when we do the comparison, we can see that A is A and B is B plus C divided by BC. So let's substitute that into the definition. We are going to have A delta B plus C divided by BC is equal to, on the numerator, we have A plus B. A is A, but B is B plus C divided by BC. So we are going to have A plus B plus C divided by BC for the numerator. Then the denominator, we have A times B. A is A, but B is B plus C divided by BC. So we are going to have A times B plus C divided by BC. When we simplify what we have in the first bracket, we are going to have ABC plus B plus C divided by BC. Divided by, on the denominator, if we simplify what we have in this bracket, we are going to have A times B plus C divided by BC. From fractions, we know that this will give us ABC plus B plus C divided by BC times BC divided by A times B plus C. So BC and BC will be gone. And so this is going to give us ABC plus B plus C divided by AB plus AC. So what we have on the right hand side is ABC plus B plus C divided by AB plus AC. What we had on the left hand side is A plus B plus ABC divided by AC plus BC. Now let's compare. We can see that on the left hand side, on the numerator, we have ABC. On the right hand side, on the numerator, we have ABC. On the left hand side, on the numerator, we have B. On the right hand side, on the numerator, we have B. On the left hand side, on the numerator, we have A. But on the right hand side, on the numerator, we have C. Now, A is not equal to C. So this shows clearly that what we have on the left hand side is not equal to what we have on the right hand side. The same goes for the denominator. If you compare the denominator on the left hand side to the denominator on the right hand side, they are not the same. On the right hand side, we have AB here, but on the left hand side, we have BC. On the right hand side, we have AC. Here we have AC. So we have BC here, but here is AB. So the left hand side is not equal to the right hand side. And so since the left hand side is not equal to the right hand side, we can say that the binary operation delta is not associative. We have considered two examples on the associative property. Let's consider the next property, which is the distributive property. If two binary operations, star and delta, are defined on the set R of real numbers, then star is left distributive over delta when A star B delta C into bracket is equal to A star B in one bracket delta A star C. So if you have two binary operations, star and delta, such that A star B delta C is equal to A star B delta A star C, then we say that star is left distributive over delta. We say that star is right distributive over delta when B delta C star A is equal to B star A delta C star A. So when star is left distributive over delta, A star B delta C is equal to A star B delta A star C. But when star is right distributive over delta, then B delta C star A is equal to B star A delta C star A. Let's apply this to solve some questions. The binary operations star and delta are defined on the set of real numbers R by A star B is equal to A plus B and A delta B is equal to half times AB. Determine whether or not star is left distributive over delta. So here we are going to determine whether star is left distributive over delta. The two binary operations are star and delta, and their definitions have been given to us here. A star B is equal to A plus B and A delta B is equal to half times AB. We have just learnt that if star is left distributive over delta, then A star B delta C will be equal to A star B delta A star C. So we are going to compute what we have on the left hand side, then we compute what we have on the right hand side, and after that we will compare them and see whether they are the same. Let's start with the left hand side. On the left hand side we have A star B delta C. So we will begin with what is in the bracket. What is in the bracket is B delta C. So we go for the binary operation delta. The definition for the binary operation delta is A delta B is equal to half times AB. So B delta C will be equal to half times BC. So then we can say that A star B delta C will be equal to A star B delta C is now half BC. So A star half BC. We can now compute this using the definition for the binary operation star. For the binary operation star, its definition is A star B is equal to A plus B. So A star half BC will be equal to A plus half BC. So what we have on the left hand side, which is A star B delta C, is equal to A plus half BC. Now let's compute for what we have on the right hand side. On the right hand side, we have A star B delta A star C. So let's begin with what we have in the brackets. The first bracket is A star B, and A star B is equal to A plus B. The second bracket is A star C. From the definition of star, A star B is equal to A plus B. So A star C will be equal to A plus C. So then we can say that A star B delta A star C is equal to A plus B delta A plus C. Now we can use the definition for the binary operation delta to compute this. The definition for the binary operation delta is A delta B is equal to half times AB. When we compare A delta B to A plus B delta A plus C, we can see that A plus B will be A and A plus C will be B. And so when we substitute this into the definition, A plus B delta A plus C will be equal to half times A plus B times A plus C. As you can clearly see, what we have on the left hand side is A plus half times BC. And what we have on the right hand side is half times A plus B, A plus C. So what we have on the left hand side is not equal to what we have on the right hand side. And so because the left hand side, which is A star B delta C, is not equal to the right hand side, which is A star B delta A star C, we can say that star is not left distributive over delta. Let's consider the next question. The binary operation star is defined by A star B, and it is equal to half times AB. Find I. A star B plus C. I. A star B plus A star C. I. What conclusion can you draw about star from your answers in I and II? Let's begin with the first part. A star B plus C. Let's compute for this. The definition for star is A star B is equal to half times AB. So if you want to compute for A star B plus C, it means that A will be A and B will be B plus C. So when you substitute this into the definition of star, we are going to have half times A times B, which is now B plus C. And when we simplify this, we are going to have AB plus AC divided by 2. Let's look at the II. It says we should find A star B plus A star C. A star B has been given to us in the question. It is half AB. A star C will be equal to half AC. So A star B plus A star C will be equal to half AB plus half AC. And half AB plus half AC will give us AB plus AC divided by 2. So as you can clearly see here, A star B plus C is equal to A star B plus A star C. So what conclusion can we draw from this? We can conclude that since A star B plus C is equal to A star B plus A star C, the binary operation star is left distributive over addition. We have considered two examples on the distributive property. Let's move on to the next property, which is the identity or the neutral element. Identity or neutral element. If a binary operation star is defined on a set R of real numbers and E is the identity or neutral element, then A star E is equal to A. If E is the neutral element of the binary operation star, then A star E is equal to A. Every binary operation has one identity element. Let's apply this to solve some questions. A binary operation delta is defined on the set R of real numbers by M delta n is equal to M plus n plus 10. Find the identity element. Let's assume that the identity element is E. Here, the binary operation is delta. So if the identity element is E, then we can say that M delta E is equal to M. M delta E is equal to M. You can also say N delta E is equal to N. It's the same thing. Let's find what we have on the right-hand side of this equation, M delta E. The definition of the binary operation delta is M delta N is equal to M plus N plus 10. So if we want to compute for M delta E, what it means is that M will be M and N will be E. So M delta E will be M plus E plus 10 is equal to M. From here we can find E, which is the identity element. So I'll send M and 10 to the right hand side. When I do that, I'm going to have E is equal to M minus 10. And this gives us E is equal to negative 10. This means that the identity element for this binary operation is negative 10. It means that if you compute any element delta negative 10, you are going to get the same element. So for example, for this particular binary operation, if you compute 2 delta negative 10, you are going to get 2. If you compute, let's say, negative 4 delta negative 10, you are going to get negative 4. If you find any element delta negative 10 for this particular binary operation, you are going to get the same element because negative 10 is the identity element for this binary operation. Let's solve another question. A binary operation star is defined on the set R of real numbers by P star Q is equal to P plus Q minus 2PQ, where P and Q belongs to R. Find the identity element under the operation star. We have learned that if E is the identity element, then P star E is equal to P. Or you can also say Q star E is equal to Q. Or A star E is equal to A is the same thing. So here we are using P and E as the identity element. So P star E is equal to P. So let's compute for what we have on the left hand side, which is P star E. The definition is P star Q is equal to P plus Q minus 2PQ. So P star E will be equal to P plus E minus 2PE. So P plus E minus 2PE is equal to P. Let's find E, which is the identity element. To do that, I'll send P over to the right hand side. When I do that, I'm going to have E minus 2PE is equal to P minus P. P minus P will give us 0, so we have E minus 2PE is equal to 0. We want to make E the subject, so I'll factorize it out. When I do that, I'm going to have E into bracket 1 minus 2P is equal to 0. We will divide both sides by 1 minus 2P. So we have E into bracket 1 minus 2P divided by 1 minus 2P is equal to 0 divided by 1 minus 2P. So 1 minus 2P and 1 minus 2P will be gone. So E will be equal to 0 divided by 1 minus 2P. 0 divided by 1 minus 2P gives us 0. So E is equal to 0. So it means that for this particular binary operation, the identity element is 0. What this means is that if you compute any element star 0, you are going to get the same element. So for example, for this particular binary operation, if you compute, let's say 3 star 0, you are going to get 3. If you compute 5 star 0, you are going to get 5. If you compute half star 0, you are going to get half, because 0 is the identity element. So if you compute any element star 0, you are going to get the same element. Let's look at the last property, that is the inverse element. Inverse element. If a binary operation star is defined on a set R of real numbers, then A star A inverse is equal to the identity element. So here, A inverse is the inverse of A, and E is the identity or neutral element. So for a given binary operation, let's say the binary operation is star, A star A inverse is equal to the identity element. So if you compute for an element and its inverse, you are going to have the identity element. What this means is that before we can find the inverse of an element under a particular binary operation, we first have to find the identity element. A star A inverse gives us the identity element. Let's apply this to solve some questions. Here's the first question. A binary operation delta is defined on the set R of real numbers by A delta B is equal to A plus B minus 5AB, where A and B belongs to R and R is closed under delta. Find under delta the A, identity element E, B, the inverse of negative 1 on 4. So let's begin with the first part, which is the identity element E. The definition of the binary operation is A delta B is equal to A plus B minus 5AB. We have just learned that if E is the identity element, then A delta E is equal to A. On the left hand side of this equation, we have A delta E. So let's compute for A delta E. The definition of the binary operation is A delta B is equal to A plus B minus 5AB. So A delta E will give us A plus E minus 5AE. And this is equal to A, as we can see from the equation here. Let's find E. I'll send A to the right hand side. When I do that, I'm going to have E minus 5AE is equal to A minus A. A minus A gives us 0. So if we factor E out here, we are going to have E into bracket 1 minus 5A is equal to 0. We divide both sides by 1 minus 5A. So 1 minus 5A and 1 minus 5A will be gone. And so E will be equal to 0 divided by 1 minus 5A, which gives us 0. So the identity element for this particular binary operation is 0. Now the question says that we should find the inverse of negative 1 on 4. Now before we can find the inverse of negative 1 on 4, we have to get the inverse function for this particular binary operation. So we first have to find the inverse function. Then we will substitute negative 1 on 4 into the inverse function to get the inverse of negative 1 on 4. How do we get the inverse function? We have just learned that for a given binary operation, so here the binary operation is delta. So for the binary operation delta, A delta, the inverse of A will give us the identity element. From here, we can find the inverse of A, which will give us the inverse function for this particular binary operation. So let's compute for A delta A inverse. The definition for the binary operation is A delta B is equal to A plus B minus 5AB. So A delta A inverse will give us A plus A inverse minus 5A inverse. And this is equal to the identity element E. And we have found the identity element E to be 0. So A plus A inverse minus 5A inverse will give us 0. We want to find A inverse, so I will send A to the right hand side. When I do that, I'm going to have A inverse minus 5 times A inverse is equal to negative A. I'll factorize A inverse out here. When I do that, I'm going to have A inverse out into bracket 1 minus 5A is equal to negative A. We then divide both sides by 1 minus 5A. So we divide the left hand side by 1 minus 5A and we divide the right hand side also by 1 minus 5A. So 1 minus 5A and 1 minus 5A will be gone. And so A inverse will be equal to negative A divided by 1 minus 5A. This gives us the inverse function for this binary operation. So for this binary operation, the inverse function is negative A divided by 1 minus 5A. So if you want to find the inverse of negative 1 divided by 4, we will substitute negative 1 divided by 4 into this function. So where we see A, we will replace it with negative 1 divided by 4. So the inverse of negative 1 divided by 4 will be equal to minus, on the numerator we have minus A, but A is now negative 1 divided by 4 because we are finding the inverse of negative 1 divided by 4. So on the numerator we have minus negative 1 divided by 4 divided by, on the denominator we have 1 minus 5 times negative 1 divided by 4, and this gives us 1 divided by 9. So under this binary operation, the inverse of negative 1 divided by 4 is 1 divided by 9. Let's consider the next question. A binary operation star is defined on the set R of real numbers by A star B is equal to A plus B plus 4, where A and B belong to R. Find I, the identity element of the operation. II, the inverse of a real number x, and III, the inverse of 5. Let's start with the first part, the identity element of the operation. The definition of the binary operation is A star B is equal to A plus B plus 4. Let's assume that the identity element of the binary operation is E. If the identity element of the binary operation is E, then we can say that A star E is equal to A. Now let's compute for A star E. The definition is A star B is equal to A plus B plus 4. So A star E will be equal to A plus E plus 4. We want to find E, so I'll send A and 4 to the right hand side. That will give us E is equal to A minus 4. So E will be equal to negative 4. So it means that the identity element for this particular binary operation is negative 4. The question said that we should find the inverse for a real number x. We know that if E is the identity element, then x star x inverse will give us E. With this, we can find the inverse of a real number x, which is x inverse. So let's compute for x star x inverse. The definition is A star B is equal to A plus B plus 4. So x star x inverse will give us x plus x inverse plus 4. And this is equal to the identity element E, which is negative 4. We want to find x inverse. So I will send both x and 4 to the right hand side. That will give us x inverse is equal to negative 4 minus 4 minus x. And so x inverse is equal to negative 8 minus x. So the inverse of a real number x is negative 8 minus x. The last part of the question says that we should find the inverse of 5. We have the inverse function here. We have x inverse is equal to negative 8 minus x. So if you want the inverse of 5, we will substitute 5 into the inverse function. So where we see x, we replace it with 5. So the inverse of 5 will be equal to negative 8 minus 5. And negative 8 minus 5 gives us negative 13. So it means that under this binary operation, the inverse of 5 is negative 13. Let's consider the next question. A binary operation delta is defined on the set R of real numbers by P delta Q is equal to P plus Q minus 2PQ, where P and Q belongs to R. A. Find the identity element under the operation delta. B. Which element in R has no inverse under the operation delta? So for the first part of the question, we are going to find the identity element. And for the second part, the question is asking us to find the element in R that has no inverse. It means that we have to find the element in R that will make the inverse function undefined. So we will first find the inverse function, then we will find the element that will make the inverse function undefined. Let's begin with the first part, which is the identity element. If the identity element is E, then we can say that P delta E will be equal to P. What is P delta E? The definition of the binary operation is P delta Q is equal to P plus Q minus 2PQ. So P delta E, if we compute it, we are going to have P plus E minus 2PE. And this is equal to P. We want to find E, so I'll send P to the right hand side, and that will give us E minus 2PE is equal to P minus P. P minus P is 0. So E minus 2PE is equal to 0. I'll factor E out here. That gives us E into bracket 1 minus 2P is equal to 0. Then I'll divide both sides by 1 minus 2P. So 1 minus 2P, 1 minus 2P gone. And so E will be equal to 0 divided by 1 minus 2P. And 0 divided by 1 minus 2P gives us 0. So E, which is the identity element, is 0. Okay. The next part, we are going to find the inverse function. We have just learned that if the binary operation is delta, then we can say that P delta P inverse will give us E. And P, when we find P inverse, that will be the inverse function for the binary operation. So let's find P inverse. Let's compute for P delta P inverse. The definition is P delta Q is equal to P plus Q minus 2PQ. So P delta P inverse will give us P plus P inverse minus 2 times P inverse. And this will be equal to the identity element E, which we have just found to be 0. So it's equal to 0. We want to find P inverse. So I'll send P to the right hand side. When I do that, I'm going to have P inverse minus 2 times P inverse is equal to negative P. I'll factor P inverse out here. That will give us P inverse into bracket 1 minus 2P is equal to negative P. So I'll divide both sides by 1 minus 2P. I'll divide the left hand side by 1 minus 2P and the right hand side by 1 minus 2P. So 1 minus 2P and 1 minus 2P will be gone. And so P inverse, which will give us the inverse function for this particular binary operation, is equal to negative P divided by 1 minus 2P. Now the question says that we should find the element which has no inverse, which means that we should find the element which will make this inverse function undefined. From our lesson on algebraic expressions, we learned that if you have a fraction of the form A divided by B, the fraction will be undefined when the denominator is equal to 0. The fraction will be undefined when the denominator is equal to 0. So for the fraction A divided by B, the fraction will be undefined when B, which is the denominator, is equal to 0. So for this particular fraction, negative P divided by 1 minus 2P, it will be undefined when the denominator 1 minus 2P is equal to 0. If 1 minus 2P is equal to 0, then we can say that 2P is equal to 1. To find P, we will divide both sides by 2. We divide the left hand side by 2 and the right hand side by 2. 2 and 2 will cancel each other out, so P will be equal to half. What this means is that when P is equal to half, the inverse function becomes undefined. So for this binary operation, the element half has no inverse, because when P is half, the inverse function becomes undefined. So half has no inverse under this binary operation delta. Let's consider the last question. A binary operation delta is defined on the set R of real numbers R by x delta y is equal to x plus y plus 10. The first part of the question says we should find the identity element, and the second part says that we should find the inverse of 3 and negative 5 under delta. So let's start with the first part, the identity element. Let's assume that the identity element is E. The definition of the binary operation is x delta y is equal to x plus y plus 10. If we assume that the identity element is E, then we can say that x delta E is equal to x. X delta E is equal to x. Let's compute for x delta E. The definition is x delta y is equal to x plus y plus 10. So x delta E will give us x plus E plus 10, and this is equal to x. I want to find E, so I will send both x and 10 to the right hand side. When I do that, I'm going to have E is equal to x minus 10, and so E is equal to negative 10. So for this particular binary operation, the identity element is negative 10. We want to find the inverse of 3 and negative 5. So first we need the inverse function. If E is the identity element, then we can see that x delta x inverse will give us the identity element, which is E. Let's compute for x delta x inverse. The definition is x delta y is equal to x plus y plus 10. So x delta x inverse will give us x plus x inverse plus 10 is equal to the identity element E, which is negative 10. We want to find x inverse, which will give us the inverse function. So x inverse will be equal to negative 10 minus x. And this gives us x inverse is equal to negative 20 minus x. So the inverse function is x inverse is equal to negative 20 minus x. So if we want the inverse of 3, we will substitute 3 into the inverse function. So where we see x, we will replace it with 3. So the inverse of 3 will be equal to negative 20 minus 3. And negative 20 minus 3 will give us negative 23. So under this particular binary operation, the inverse of 3 is negative 23. To get the inverse of negative 5, we will substitute negative 5 into the inverse function. The inverse function is x inverse is equal to negative 20 minus x. So we replace x with negative 5. So the inverse of negative 5 will be equal to negative 20 minus negative 5. And negative 20 minus negative 5 gives us negative 15.